magnetic boundary conditions. So just like we have discussed the boundary conditions when there are two different dielectrics, okay, here also when there are two different magnetic materials of different permeabilities, right, mu1 and mu2, let us say, okay, and this is the boundary, then what will be the magnetic field in each of these areas, each of these regions, okay. So for this we are going to make use of two equations. One is called as one is B bar dot ds bar, this is equal to 0. We have already discussed the flux through any closed surface is going to be 0, the closed surface, okay, not any surface but a closed surface. So this is, it is often called as the Gauss law for magnetic fields, okay, Gauss law for magnetic fields. This is one equation, and the second equation is closed integral h bar dot dl bar, this is equal to the enclosed current, this is the Ampere's law, right. So these are the two equations that we are going to use, okay, to derive the magnetic boundary conditions. So here we will take the boundary again here once again. This is the first region, the second region has permeability mu2, okay, and the magnetic fields we can take here. If it is B1 bar, the tangential component is going to be B1 T bar, and this is B1 N bar, the normal component, okay. Similarly, if this is B2 bar, then this is the normal and this is the tangential component, B2T bar, and this is B2N bar, okay. So here we are going to take one cylindrical structure, okay. So this we are going to call it as the Gaussian surface. So its height is delta h, it is almost 0, delta h almost tends to 0, that is the Gaussian surface that we have taken. Now what is the first equation? The Gauss law is integral b bar, the closed surface integral b bar dot ds bar is equal to 0. Now if you see this Gaussian surface, it has one curved surface area, one top surface and one bottom surface, okay. Now this curved surface area, if you take in the region 1, the tangential component is going to enter into it perpendicularly, but it is entering and it is also leaving. So what will be the net flux? It is 0, okay. Similarly, if you take B2T, it is also entering and it is also leaving. So the net flux because of B2T is 0, okay. So B1N and B2N, they are the normal components. So the curved surface area is this, and the normal components B1N and B2N are in this direction. So they won't have any contribution. So in this way, the total flux because of this curved surface area is 0. Now if you see the top surface, okay, now B1N bar is coming out of the top surface, okay, and the bottom surface B1N we don't require now, B2N is entering the bottom surface, it is entering into the surface area, right, into the Gaussian surface. So the dot product of B1N bar and B2N bar with curved surface area will be 0, right. This is because they are perpendicular to the normal surface vector, okay. So this is one point we discussed, and what is the other point we discussed? B1 T bar and B2 T bar are entering and also leaving the curved surface area, exiting the curved surface area. So their contribution is 0. So the only contribution that is left is because of B1N through the top surface and B2N through the bottom surface. Okay, so if this area, the top and bottom surfaces, the area if you are taking delta S, okay, then you can write down integral closed integral B dot ds bar is equal to 0, right. So it is a closed surface integral. Okay, so 1 is because of the contribution of B1n through the top surface, so it will just be the product because the magnetic field is perpendicular to the surface, or you can say parallel to the normal of the surface, top surface. Okay, minus B2n delta S. Why minus? Because B2n is entering. Okay, this is leaving the Gaussian surface and B2n is entering the Gaussian surface. So that's why we are attaching a negative sign. Okay, so if this is equal to 0, then delta S and delta S will be cancelled. So finally you are going to get B1n is equal to B2n. Okay, so the vectors are going to be equal, or you can write B1 n bar is nothing but mu1 h1 n bar is equal to mu2 h2 n bar. Okay, so this is one boundary condition. Now the second boundary condition, what about the tangential component? So here we have information about the normal components. So next we will see how to get the relationship with the tangential components. Okay, so we will take the surface once again, the boundary once again. This is region 1, permeability is mu1, and this is region 2 with permeability mu2. Okay, just like in the previous case, we are going to take H1, the magnetic field intensity, because now we are going to apply Ampere's law. Okay, so this is H1 n bar, the normal component, and this is the tangential component. Similarly, here you have H2 bar, this is the normal component, tangential component, H2 t bar, and this is H2 n bar. Okay, now what you do is you take a Amperean path like this. Okay, now whenever there is an Amperean path, we are also concerned with whether there is any current enclosed by it, right. So that is why we will take the case of the current density through this boundary. Okay, so if there is no current density, it will simply be 0, but if there is a current density also, what will be the case? So we have to derive for both the conditions, right. So we have a current density, let us say surface current some K value. Okay, surface current is K ampere per meter. Okay, and this loop we will name as A, B, C and D. Okay, and the line integral we will take in this direction. Okay, so now what is the Ampere's law? The Ampere's law is given as integral H bar dot dl bar is equal to the enclosed current. Now here we have the dot product, that means wherever H bar and dl bar are perpendicular to each other, it will simply be 0. So now if you take AB, okay, this AB is parallel to H1 t bar, but it's perpendicular to H1 n bar. Okay, so we can write H1 t into this length. Okay, so this length we will take as delta W, let us say, and this height we will take as delta H. Okay, so now if you apply the line integral, first along AB if you take, then you are going to get, or we can write AB plus BC plus CD plus DA is equal to I enclosed. So first we will write the integral AB. Okay, so this is going to be H1t into delta W, the magnetic field intensity which is parallel to the length vector into the length is delta W. Okay, plus this is for AB. Now for BC if you take, now BC has two parts. Okay, so in the region 1, let's say this length will be delta H by 2, so because we are taking symmetrically. Okay, so for this length only, what will be the magnetic field that is present parallel to it? H1 n bar. H1 t bar will be perpendicular, so there is no contribution because of H1 t bar along BC. Okay, so one half of it you're going to have minus h1n, because h1n and delta h, the length vector, are in the opposite direction, right? So h1n into delta h by 2, and again here also when you're going in this direction, in the bottom region, the second region, delta h by 2 is the length and h2n is in the opposite direction again. Okay, so here you're going to get minus h2n into delta h by 2. This is because of BC. Okay, and then because of CD, again what will be the vector here? This is the length vector delta W, and the parallel vector, parallel magnetic field component is h2t, but it is in the opposite direction. Okay, so you're going to write it as minus h2t delta W. Okay, then plus dA. In dA, if you can see, the length vector is in the same direction as h2n and h1n. So here you're going to get positive sign only. Okay, so h1n or h2n into delta h by 2 plus h1n into delta h by 2. This is equal to the enclosed current. So here we have taken K to be the surface current in ampere per meter. Okay, so the enclosed current will be K into the length, the total length, right? So this is the current per unit length. What is the entire length here? Delta W. Okay, so here you're going to get K into delta W. Okay, so here this term and this term is going to get cancelled. Here this term and this term is going to get cancelled. So what you're going to be left with? You're going to be left with h1t delta W minus h2t delta W is equal to K delta W. So this means that h1t minus h2t is equal to K. Okay, so this is the second boundary condition, or you can also write as B1t by mu1 minus B2t by mu2 is equal to K. Okay, so this is the other expression. Now here we have written in terms of the tangential components. Okay, but it's more convenient to write in this manner. Let us say h1 bar is in region 1, so it's not the tangential component, the entire component we are taking, minus h2 bar cross an12 bar. Okay, this is equal to K bar, because the surface charge current is a vector, right? So it is useful for us if we know the expression in terms of the vector quantity. Okay, so this expression will come in more handy. You can verify it. The directions you can verify. H1 is in this direction, H2 is in this direction. If you cross product this with an12, here you need to know what is an12. This is the normal vector to the boundary starting from region 1 towards region 2. Okay, this point is important. It is from region 1 to region 2. Okay, because if you take the boundary here, if this is region 1 and this is region 2, then this is going to be the normal vector an12 bar. Okay, so if you are drawing in the opposite direction, then it is going to be minus an12, right? So this point is important. The vector should be from region 1 to region 2. So if you verify, you're going to get the same result as this. Okay, so basically this direction, if you can see, for this current density, the current density is into the plane, right? So for this current density, if you apply the right hand rule, you will see that the magnetic field is in this direction. That is why here the enclosed current we have taken positive values. If it was coming out of the plane, then we would have taken minus K delta W. Okay, so but in order to ignore all of that kind of confusions, we can just remember this equation. Okay, so this will work better when you are dealing with the vectors. Okay, you don't have to consider the directions, then you just have to substitute, okay, the respective directions. So if there is no surface charge density, then what will happen? K bar is 0. So in that case, H1 T bar is simply going to be equal to H2 T bar. Okay. If no surface current, then simply H1T is equal to H2T and B1T by mu 1 is equal to B2T by mu 2. Okay. So you can put it in the vector form.